Okay, so welcome to this AICAT CAST Division webinar. We have the privilege of hearing today from Dr. Peter Schmal, and he is the Principal Application Engineer and Head PSE Academic Process Systems Engineering. And I just want to mention just a couple things about Dr. Schmal. He has a PhD in large-scale dynamic modeling, and he graduated from the University of Technology Delft in the Netherlands. And after his PhD, he had kind of an interesting career path here. He started his own company to commercialize a patent on new separation methods. And after 2 postdocs, then he joined PSE as a consultant in 2008, has been working in New Jersey, moved to New Jersey in 2010. So we're really pleased to be able to hear from Dr. Schmal. He's going to be talking about some of the latest developments with gPROMS. And many of the people on this call, including myself, have had experience with gPROMS and have been very impressed by the potential for simulation and also optimism.
Yeah, thank you, John, for this very kind introduction, and welcome. For some of you, it's very late at the moment, I understand. In this presentation, I'm going to give a little bit of a background of PSE. I'll keep that short for the people who are not familiar with PSE. And then I'll give a bit of an overview of what we have done with gPROMS over time, so to speak. I'll give you a little bit of an idea of the latest developments, and then I'll go into 2 case studies, one focusing on optimization and the importance of model complexity there, and the second one is another optimization example where we show the benefits of having accurate models and optimization capabilities. So for those who are not too familiar, PSE started in Imperial College, and our managing director, Kostas Pantelides, is still a part-time professor there. And many person years were spent before the first commercial version of gPROMS came out in 1997. PSE is a private independent company incorporated in the UK, and today we have offices shown on the top. So our headquarters are in London, and this is also where all our developers are based. And I'm based in our New Jersey office in the US, and we have agents in the bottom rows. We're about 120 people at the moment, with more than half of them being PhDs. Besides supplying software, we also supply services, and this means that we can do whatever people want. This can be anything from us writing a report and just giving you a report of the design and operation of a chemical plant, all the way up to where the customer is doing all the work, and we are hired for detailed questions from time to time. As I show you, we are in many different sectors, and we traditionally have a strong background in R&D, research and development, but we're moving into commercials. We won the Royal Academy McRobert Award for Engineering Innovation, which is UK's highest engineering award. It's rarely given to a software company and rarely to a small company, and at the time we were a very small software company, so we're very proud of that. Our business is what we call advanced process modeling. And the question obviously is, okay, that's a nice catching phrase, but what do we mean by advanced process modeling? Well, during normal operation or design of a plant, there's a lot of decisions that you're faced with, ranging from equipment configuration, catalyst choices, operating policies, etc. And ideally, you want to make those decisions based on accurate quantification. And for that purpose, you would ideally want to have largely first principle models. In chemical engineering, we'll always have some gray elements, so to speak, empirical models. You want to be able to validate those models against your plant data. You want to be able to do rigorous optimization in contrast to optimization by simulation, basically. and you want to be able to implement your own procedures through a task language. So what we try to do is give you the opportunity to explore the decision space very rapidly, reduce the uncertainty so that you can make better, faster, and safer decisions in your operations. Now, PSC is organized along different sectors that you can see here, and our aim is to define, develop, and drive the adaptation of next-generation modeling technology, methodologies, and workflow. So we help on both the modeling, the methodologies, and the workflow. And our goal is to bring transformations to each sector that we enter. Before 2010, we were mainly focusing on R&D, and now we're trying to move into engineering and operations. And for that to really work, you need to have an engineer-friendly tool based on what we call the gPROMS platform. And at this moment in time, I forgot to mention that we are heavily investing in this platform. So in 2014, about a third of our revenue was spent on improving the platform, which is obviously a very significant amount of our revenue. So all our products are based on this platform, and the most familiar to you most likely is gPROMS Model Builder, which is a general mathematical modeling platform that allows you to implement your own equations, make them flow sheetable, create your own flow sheets, custom flow sheets, etc. We also have some sector-focused modeling tools that you can see here. The gProcess or Process Builder is a product that we are beta testing at the moment, and it is advanced process modeling, process simulation for the chemicals and petrochemicals industry. So it is the typical kind of models that you would find in packages like Pro2, HYSYS, Aspen, etc. But what we aim to do is take them one step further than you're used to. This platform, we can, since it's an open platform, we can actually use different materials modeling packages. Our standard has always been multi-flash, which is basically the standard physical property package for all your physical property calculations in gPROMS. But we recently acquired GSAFT, which stands for Statistical Association Fluid Theory from Imperial College. And this can really be considered to be the next generation of group contribution methods. And if you're interested in this or any of these packages, please visit our website and you can get a lot more information on them. We also can connect to OLive for electrolytes and other internal packages because that is fairly easy to do. We can also export our models to be deployed behind the web, for instance, or behind an Excel interface or your own interface. We can connect to MATLAB, CFD, and we're CAPE Open compliant, so that means you can put gPROMS inside Pro2, for example. Now, if you look at the history of gPROMS, I figured this was nice because some of you may have seen gPROMS along this timeline. We started in 1998. It was a command executable. You had to enter your models in text form in a text editor, and that is how you run your models. And the first version I used was 1.8.4, so I almost went through the whole line that I'll show here. In 2001, in gPROMS 2.0, we introduced an editor in our product so that you didn't need to have a separate editor and you could run from this single unit, so there was no need for a command prompt anymore. In 2003, we introduced flow sheeting capabilities and color coding, which makes reading of the text much easier. In 2007, we introduced dialog boxes, so you could double-click on an icon, make a unit specification in the dialog boxes. In 2010, we introduced, one of the key things we introduced was initialization procedures. And over time, I'm just giving you a view of what it looked like. but we did a lot of things on the solver as well. So our developers, we have half of them basically working on the solvers, half of them working on the user interface. And what I'm showing here is mostly the user interface, but in 2010 we introduced initialization procedures, which is a technique that allows you to initialize your model from any initial state that you guess, to any reasonable operating condition. And this is a key feature for simultaneous solvers, like gPROMS compared to sequential solvers such as Pro2, HiSys, Aspen, etc. In 2014, we've had a major push on usability. So now the user gets a lot of messages of missing connections, missing specifications in dialog boxes, to really help the user. As I said, in this slide, I mainly give you a feel of what you see as a user, but behind the scenes we've done a large number of things. And just to give you an idea, this is the latest developments compared to 3.7, which was the previous version of gPROMS. And in PSE, we always like to distinguish between two types of, or actually three types, but for this presentation, two types of users. Tier 1, which are the model developers, and Tier 2, which are the flow sheeting users. And as you can see here, I'm not going to talk through all of these cases, but just to give you an idea of all the things that we have been working on and have been adding. I'll focus on one that has been released, what we call model pruning. And what happens is that I've got a flow sheet as shown here, and I set up an optimization problem, or sorry, I look at the size of the problem. The original problem is about 50,000 equations for this particular flow sheet. We have a feature that we introduced quite a few years ago. It's called identity elimination. So every equation that is of the type y is x, we will remove automatically, and that will speed things up significantly. And then we've got a feature called model pruning, which removes all the variables that can be post-calculated. Now, for simulation, that doesn't make much of a difference, but if I would set up an optimization problem, as shown here, where I would mainly be interested in to maximize this product flow, and I've got constraints on this side of the process, and I don't worry too much about this side because it's over-designed, for example. If I would do that, gPROMS would automatically ignore this part of the calculations and thus would reduce the size of the problem very, very significantly. And this is one of the things we've introduced. So besides the user interface, there's actually quite a lot behind the scenes that we do. Okay, this was a brief introduction into our company and our software. I'll now move on to discuss two case studies. And the first one is the effect of model complexity on startup optimization. What we see in literature and in practice is that people tend to simplify the process models when they start to do optimization to reduce the CPU. Because obviously optimizations take much more time than simulations. But by doing this, we obviously sacrifice some accuracy, and especially if one of the constraints has to do with safety, this may be very dangerous. So what do? Do you focus on setting up a more complex optimization problem, which obviously will give you hopefully a better result in the sense of a better objective? But if you usually have to use simpler models to do that, because you pay a penalty somewhere. We just usually have some sort of CPU usage we want to use, and we can focus that on the optimization problem or the model. And obviously, the other way to do it is say, no, I want very accurate models, but then I have to compromise, if you will, on the optimization problem. So the question that then arises is, what is the effect of model complexity on the optimization outcome? And to investigate this, I looked at this optimization of startup of this process, and I actually looked at what is shown in this box, so not the whole plant. And I'll briefly talk you through this process. It's propylene oxide reacts with methanol with the use of a catalyst to form MP2 and MP1. And MP1 is further reacted in the second part of this process to NDP and higher products. Now, this reactor is set up in such a way that it's an exothermic reaction, so the heat of reaction is used to preheat the feed. And obviously, when you start up this kind of process, you basically have two options. One, you could use a preheater, or in this case, what I've done, I'm using the condenser basically of this first column as the heater for this process. So what we'll do, we'll feed the process, put the column at high pressure so that we can warm up the reactor, and once the reactor is warm enough, we'll add the PO and the catalyst to get the reaction started. Now, since this is an exothermic reaction, there's dangers of runaway, so we need to keep the temperature under control. There's a large recycle flow coming back because the methanol is not only used as one of the reactants, but it's also a heat sink to grab all the heat. And in the second part of the reaction, we're actually generating some steam during normal operation. Now, the final thing to note is that this is a very high purity column. The purity of methanol coming out of the top is more than 99.99% high, so it's a high purity column. Now, to investigate the effect of the model complexity, I considered a detailed and a reduced model for the reactor and the distillation column, giving me 4 different combinations. So a detailed reactor and a detailed distillation column, detailed reactor, reduced distillation column, reduced reactor, detailed distillation column, etc. Now, I'm not going to talk through the equations that I used, but just to give you the key difference in the reactor was that the detailed model considered a full momentum balance, considering density changes, whereas the simplified reactor actually didn't consider the effect of density changes on for instance, velocities and process in the reactor. For the distillation column, the detailed model took into account weeping, vapor through the downcomer, all those kind of effects, where the reduced model completely ignored those. Now, in this process, there's a lot of stages that are considered. And just to give you an idea for the people that are not too familiar with distillation, the column started completely empty, filled with nitrogen, because PO is very flammable. So rather than having air in this system, you'll have to fill it with nitrogen. And in the beginning, the tray is empty. Then liquid starts to pour, usually from the condenser, but it could also be from the feed or both. And what you will see is that there's mainly weeping, and if the reboiler is turned on, you will actually see that the vapor is traveling through the downcomer as indicated here. At a certain point, there will be liquid sealing, and that will stop the vapor from being able to travel through the downcomer, and this will create a sudden increase in the pressure difference. And then finally, once you're in normal operation, weeping has basically stopped. I modeled this as 4 different phases, which are shown here. So we had the nitrogen purge phase in the beginning, and note this is a logarithmic scale here, because that's only very short compared to the whole startup time. And you would have things like vapor through the downcomer and weeping indicated by these yellow boxes. Then the column would be brought to high pressure to preheat the reactor, and obviously from this point on the heating of the reactor is happening. Once the reactor was warm enough, we started feeding PO, indicated for the base case in this area, and at one point we start the flow from the reboiler, and once we are in the steady state phase, we started generating low pressure steam. So here we see a Pareto curve looking at the danger. In this case, this was the PO breakthrough, because that's a very dangerous component, versus an economic objective. And the first thing to note is that the base case was set by two industry experts on startup. They defined that process, and that resulted in this point. As you can see, for the same level of danger, we could have saved a lot of money, or for the same money, we could have been much safer. And what we typically see is during startup, people tend to be very cautious and think they need to do things slowly, but that can actually lead to dangerous situations. And that is something we typically saw here. The other thing we see is the different results for the different model types. So RCRR means reduced column, reduced reactor, and you can see the different results. Now, the interesting thing was that if you look at these results, then we see that for different levels of detail, we found the same Pareto point. So the same level of danger and the same economy. So you would think we would be happy to use the simpler model, which obviously was much faster. But it turned out that these two different models gave different control profiles. And that is obviously something that we would not like to see. And to illustrate the effect, I show here the actual profile in the steady state, or close to steady state, I should say, at the end of the optimization. When I use the reduced models for both the reactor and the column, this is what the black line shows what is predicted by that model if I use the control profile generated by the optimization for that model. But if I use that control profile from the reduced model in the detailed model, I get the red line. And there was a safety constraint at this point, so you can see that actually, although the original reduced model says I'm staying in the safe area, with the detailed model, I actually see that I am violating my safety constraints. So this is a very dangerous situation, and the conclusion is be careful with simplified models, or what we prefer to do at PSE, make sure you validate your models to avoid these kind of things. That brings me to the second case study, which is a Repsol whole plant optimization, where we included the detailed modeling and the validation of this particular model. So in this process, we are looking at hydrogen peroxide route to propylene oxide. This new process addresses some problems with the conventional process, in the sense that there's no styrene co-product being formed, and it therefore has less byproduct. Obviously, there's some danger in the sense that water can react with propylene oxide, but it definitely has some benefits. So once you have selected a route that you want to take, the question then becomes, okay, how do I get there? And this is where we stepped in. So the new process had a multi-tubular reactor. It had many distillation columns and two major recycle streams. So this was not a trivial case. So we were originally only hired to assist with the reactor modeling, and we started this as what we consider to be a traditional PSE multi-tubular reactor design project. And what we typically do is we look at the kinetic model from a single tube pilot reactor experiments. We determine the kinetic parameters. We may do some experimental design and additional parameter estimation so that we make sure we get the right kinetics. Once we have the right kinetics, we can do the reactor design, which is done in optimization. And then we typically do a design validation with a fluent gPROMS hybrid model simulations, where gPROMS and fluent are connected to each other and talk to each other, so to speak. Obviously, for a process like this, we perceived an opportunity to do this simultaneously, because if I improve the reactor, obviously my separation section will be different. So we considered considered both of these together. Now, when we stepped in, they actually already had done some work in a traditional flow sheeting package, Aspen Plus. They had difficulties with adjusting the thermodynamic models based on the experimental data that were available. They had difficulties in converging the flow sheet with recycles, even after small changes in the specifications. And what they did to optimize this process, they changed 2 to 3 variables at a time, sequentially, and many person days were devoted to improve separation design, basically by trial and error. Obviously, this didn't result in an optimal solution. So what we did, we have the AML FBCR, which stands for Advanced Model Library for Fixed Bed Catalytic Reactor. And in this case, we considered a 2-dimensional tube, axial and radially distributed, and 1D catalyst particles. So at each position, we could see what is happening inside the catalyst. And the reason we did this is that this was a liquid phase reaction with, which had very low diffusion coefficients, which meant that we had intraparticle transport limitations or mass transfer limitations. And in those cases, it's very important to consider these limitations in the model. On the shell side, we use well-mixed compartments in series to represent the different compartments between the baffles, but we used distributed heat transfer connections to the tube. And this was basically done using our library, which is an off-the-shelf product, so we didn't have to do any model development for this. With regards to the separation section, we used equilibrium models, equivalent to what you find in flow sheeting tools like Pro2, Aspen, HYSYS. And in 2 columns, we considered reactions, so they were reactive distillation columns. We had an azeotropic column, and the material factors and chemical engineering plant cost indices were used to adjust the capital cost estimates. Now, to identify the key process parameters, we looked at a single tube pilot reactor with cooling jackets. We made a very detailed model of the experimental rig. In some cases, we see people use simplified models to represent the pilot or lab scale. But it's actually very important to use the correct models, because if you estimate parameters on a simplified model and use them in a detailed model, things may go wrong, obviously. We performed the parameter estimation. We assessed the parameter accuracy. In this case, we were not satisfied, so we actually designed some subsequent experiments in this case. And in the end, we estimated both kinetic and heat transfer parameters, and we used about 60 experiments to do this. Now, when you do a project like this, as I indicated, there's some trade-offs, not only in model complexity, and I'll come back to that, and the optimization problem, but also between reactor and separation economics. And in this case, it really made sense to do this simultaneously. But what decisions to make? As I showed you, we are using quite complex models. So compared to definitions in global optimization techniques or superstructure optimization, we cannot take into account a huge amount of variables, but not many more than 2 to 3, as we shall see. So in the reactor, we looked at decision variables like the reactor diameter, the tube length, the baffle window size, the baffle span, but also things like coolant flow rates, coolant temperatures, etc. Since gPROMS can handle mixed integer and nonlinear programming problems, we can actually also include the number of baffles in the reactor. On the separation side, we looked at things like reflux ratios, reboiler ratios, product specifications, some constraints obviously, a number of trays, feed locations. These are all things that we can consider. Now, the objective in this case was to minimize the total annualized cost of the production, which is a combined CAPEX OPEX objective. We had constraints on quality on the product, obviously. Some of the impurities could only be as high as ppm levels. We had obviously safety constraints, coolant supply and return temperature constraints, and some of the coolants had to be returned to the environment, which have their own constraints. Effluent concentration constraints, reactor shell side velocity constraints. On the one side to prevent the tube from fouling, so the velocity had to be high enough, and on the other side to avoid excessive vibrations. So it had to be lower than a certain minute. And finally, on the reactor and column dimensions, in this respect you can think of if the plant is located at a location where the reactor has to be transported and it has to go underneath a certain bridge, then obviously that limits your reactor size. So what we did, as I said, was a simultaneous design approach where we looked at both the reactor and the separation section, where we had significant recycles that we considered. Now, we used detailed equipment models to ensure that the design reflects the true process economics. So we've done model validation to make sure that we match the equilibrium properties in the columns, the kinetics in the reactor, and obviously to make sure that we satisfy all important constraints. And in particular, safety constraints is something where you want to make sure you use a model that really reflects reality. We applied rigorous mathematical optimization, and if you, in this case we had 49 continuous and discrete decision variables. And if you wanted to try to do that by hand, there was no way that you could have done this. Making sure that you increase your objective while satisfying your constraints with 49 decision variables in a 49-dimensional space, and that is something we cannot do manually. So that is obviously all very nice, but what did this result in? Well, we ended up with a process design that met all the constraints. This is obviously inherent in our process. Once we find a solution that is optimal and satisfies all the constraints, we're in good shape. There was a lot of confidence arising from the detailed models and the formal model validation project we went through for both the reactor and the columns, which meant this was a very good basis for detailed engineering and operational support. We achieved very large reductions in annualized cost, tens of millions of euros per year, compared to the base design that they had done before. We were able to eliminate 2 columns entirely, and we saved 5 million per year by being able to remove 1 column alone. And finally, due to the heat integration that was also considered, we managed to get significant operating cost savings, which had a very attractive return on investment, which resulted in a payback of less than 4 months. Those were the 2 case studies I wanted to present. I was giving a slot of 35 minutes, and I think I've overrun by 1 minute, but I'm happy to take any questions. oh. Can anybody hear me?
Oh, you know what? Mine was still on mute. I was talking, but I was on mute there. But thank you so much for that presentation, and you know, I especially appreciated that timeline that you showed at the beginning, the development of the gPROMS and how it's evolved to solve you know, more complex and get the software into either technical users or end users' hands. Let me have you do this with just starting the discussion. If you can, in the chat window, just put your name, affiliation, and some of the things that you're interested in terms of research areas. That'll just help us you know, show where the chat window is, and then if you'd like to type questions there, you're welcome to place them there, or you can unmute your microphone and go ahead and ask some questions. We have one question from Steve Zitney. He is at the National Energy Technology Laboratory. He's researching dynamics, control, and optimization of advanced energy systems. And his question is, can you please describe any new recent developments in PDE modeling and optimization in gPROMS?
Thank you, Steve, for that question. With regards to PDE modeling, we have it's basically a general solver. What we do behind the scenes is we use the method of lines. So automatically, all our PDEs and integral equations are discretized, and we solve that. So in that sense, all the improvements we have made with regards to speed, model pruning that I showed, it doesn't only improve the speed because the blocks become smaller or the equation set that you're solving becomes smaller, but it also helps with the robustness. Now, with regards to specific things that we have done for PDEs solving, we have a non-uniform grid. So we included non-uniform grids. I think we introduced that probably four years ago, if my memory serves me right, which allows you to specify the grid either manually, and this could be beneficial if you have measurement locations at very specific locations, or if the profile is very steep in the beginning, you could just use a non-uniform grids to automatically move the grid points have more grid points at the point where it's very steep. Those are the key things with regards to our partial differential equations. Now, with regards to optimization, we have mainly been working on robustness, and including more handles for the user to allow to tweak the optimization solver. And we also introduced a new optimization solver, in optimization terminology, we like to think of dynamic optimization as, well, a dynamic optimization where the controls vary over time, or the decision variables vary over time. A point optimization in this terminology would be what we chemical engineers normally call a steady state optimization. So we would have a steady state model and we optimize that. We have a new solver that basically is a steady state optimization, but it is on a dynamic model which allows you to integrate from one steady state to another, while not taking into account the sensitivity integration during this time. So that speeds up things drastically. And those kind of solvers are particularly useful if you have a very complex model. For instance, like in this Repsol case, we didn't use it, we didn't need it, but we have had very complex processes where they wanted to optimize the design, and to move the model from one steady state to another with a jump was too much to ask for this particular model. So in that case, that solver could really help us out. And to give you an idea, I didn't mention any numbers, but we are breaking the 1 million equation barrier models from time to time. It's not regular. We typically do models of 100,000 equations, that order of magnitude, but we start to break the million equation size. Hope that answers the question, Steve. Okay,
great. So let me just follow up with one of the comment. When I was at UT Austin, you know, there were two researchers who were essentially working on parallel projects with reactive distillation, and you know, one of them used gPROMS and the other one used something else. And the one that used gPROMS was able to finish, you know, much faster than the other one that was doing another project. I saw you have a lot of, you know, applications here in distillation, separation. That seems to be a strong suite of, you know, of tools and models. You had a slide there that mentioned, you know, some of the other model, you know, pre-built models or toolboxes that you can use with gPROMS. What's the extensibility of gPROMS in terms of programming in you know, new packages for new areas?
That's a very good question. Thank you, John. Since all of these packages are built on the same platform and they're actually interchangeable, you can use our models and connect to our models, but you can also write your own models. And so you could have, for instance, suppose you, for some reason, want to have a specific reactor. You model that yourself, but you will use all our distillation column models or all the utilities from, for instance, Process Builder. And again, Process Builder is in the beta testing phase at the moment, but we should release that somewhere next year. That is something you can easily do. A lot of our customers, they actually have fully customized libraries that they have developed in-house in gPROMS, and they still use some of our models for the utilities, but they have proprietary in-house models that they developed. And if you wanted to push this very far, you could even say, well, I want my own user interface. So basically, since everything is built on the same platform, you could have, let's say your company is called My Company, to keep it general. You could create, if you wanted to, a My Company with your particular interface, with your help, with your specifications. So we are very, very flexible in the sense of what you can do. Obviously, there's associated costs, so it's not something you could do with a standard license. But we do allow you to use the models from different packages, as you see on this slide. You can add your own models to this and connect them up. Obviously, you would need to have the information streams to connect them up, but that is something that is fully documented, and we would be able to help you with how to set that up.
Great. Okay. So any other questions from the audience that you might have? You're welcome to put it into the chat window or unmute your microphone if you'd like to ask a question. Okay, so we have another question here from Jaffer Gauss from McMaster University, and he says, okay, so he works on flexible poly generation and energy systems modeling. So his question is on PDE modeling. In gPROMS, the boundary condition specification is considered by default as the initial condition, also too, for that boundary point. Why is it that way? Usually the initial condition is valid for all z, while the boundary condition is applicable only at t greater than 0. Okay, so I'm just going to go ahead and put that into the chat window.
Yep. Yeah, I think, yeah, please do, and I'll quickly read the boundary condition by default two for that boundary point. So, I mean, there's the strict mathematical sense. We would indeed need to consider the whole domain, but in numerical implementations, if you would implement this in any kind of solver, you will always need the 1 point to represent your boundary. So that is an artifact, if you will, of the numerical process. So what we do is you can specify your boundary condition, and maybe I should point out one to be absolutely clear. We chemical engineers, we tend to associate boundary conditions with those for the independent domains other than time, whereas mathematicians consider boundary conditions or initial conditions, what we consider to be only for time, to be a subset of boundary conditions. So to clarify that, I will speak in initial conditions, meaning a boundary condition for time, but it's always at the initial boundary, so that's why it's an initial condition. And I will talk about boundary conditions when it's everything but time. And in that way, so for boundary conditions, we need this one point, whatever boundary we choose. And that means that since this is an algebraic equation for the boundary condition in most cases, this means that the initial conditions only need to be specified what we call inside the domain. So yeah, there's a numerical implementation reason why this is happening. But if you look at it strictly from a mathematical point of view, you're right. You should specify an initial condition for z is 0, for instance, if that's where you specified your boundary condition.